So in this case, I want us to consider another typical exam. This is an example that we are going to have. It's not exam question, actually an example that we are going to see that is important in the calculations of a half wave and a full wave, considering what? A shunt capacitor filter. So in this case, we are given that is a transformer, steps down AC supply from 240 volt, 50 hertz to 48 volts. These are two voltages that we're given from the transformer. And as we do understand that from the transformer, we're going to have the primary and the secondary. So it is, take note, it steps down this voltage, which is our primary voltage of 240 to 48 volts on the secondary voltage, on the secondary side, which is 48 volts at a frequency of what? Of 50 hertz, which is connected to a rectifier through a shunt. We are told there, a shunt capacitor filter. We are given that. It's a shunt capacitor. So in this case, we're not going to refer to say how there is, we know that, how the resistor and the inductor, how the resistor and the capacitor are connected, because already we're given. So we do understand that the load resistor and this capacitor will be connected in what? In parallel. So we are given a load resistance that is of 440 ohms. And while the capacitor is a value of, so the capacitance that is 4400 microfarad. So the question was, calculate the following when the rectifier is used as a half wave or B as a full wave. So there are two things that you have to consider there when it is to be taken as a half wave. So this side we are going to consider for a half wave. All right. So this side, let us consider for a full wave. So the question is, what is going to be calculations? We do understand that we are referring to a shunt. That's a shunt capacitor that we have filter. All right. So let us take this information and try to answer our questions. This is what we just have, as we do understand from the formulas that I had, even the diagrams here. Let me just also present so that you do understand also your diagrams. Remember, on our diagrams, I also presented that you can have this part of your connections for a half wave. What is important that we have the capacitor and the load resistor being in parallel. That's for a shunt, and also considering your formulas in that case, we are going to consider both in that case. All right, so let's consider the first question that we are given, which is to calculate the output voltage, which is our VDC. So the output voltage, as we can see, there are so many formulas, but with the information that we have, what is it that you can consider? We have got the load resistor, we have got the capacitor, the frequency in this case. So if you are to consider this is at the output, and as I said, from the transformer, the values that you are given from the transformer, these values, they represent what we refer to as the RMS value. So this is an RMS value for the primary voltage and also for the secondary voltage. So meaning to say, from the secondary side, since we are considering all these calculations taken from what? From the output. They are from the output. So you work with the secondary side so that at least you can obtain the maximum voltage. So we can apply this formula here, because we can see that from here, we cannot work with these two formulas. We are limited of these two formulas. But if we are to consider this part of our formulas, we can win, because we have got the resistance, the load resistance, the capacitor, the frequency. What we just need is to obtain the maximum voltage in that case. And like I said, the maximum voltage is going to be affected, is going to be taken from the secondary side of the transformer. This is an RMS value, but what we need is the maximum value. So how do you calculate? Because this is going to be the same for the maximum value, as we do understand that this is exactly the same way that you calculate here for both of the half wave and the full wave. The way that you're going to calculate the maximum value here is the same from your RMS value, or you can use this formula direct. That is, the maximum value is 1,414 of the RMS value, or you can work it from this formula of the RMS value, depending with the way that you do understand. But in this case, as we can see, it's going to be the same for both. So I'm just going to calculate it from one side, but that is the same calculation that you are going to have for both full wave and a half wave. So we saw that we can calculate first the maximum voltage here. All right, so let's start by the maximum voltage. That is 1,414 of the RMS value in that case, which is from the secondary side of the transformer. Like I said, these are RMS values. So you must be very careful, because some other books, they will give you that and take it to be the maximum value, which is not supposed to be like that. Those are RMS values unless stated. Otherwise, they are supposed to state, not to assume that this is your maximum value. So you're going to multiply to 48 in that case to obtain the maximum value, which is going to give us 67,872 volts. So there we have got the maximum value at the output side. At the output side, at the secondary side. And this is the same as what you're going to even have on a full wave. So with the maximum value and with the RL, since I said these are the two formulas here, like I said, we are focusing with these two formulas that I indicated here. That's why we are focusing on what? On calculating of the maximum value because of this. So from a half wave, this side, remember this side is of a half wave. The formula is going to have a 2. On the side of a full wave, we are going to have a 4. So these are the two formulas that we are going to use differently because they are different. So meaning to say that we have got different values there. But what is the same is the maximum value for both is going to be the same. So here, whatever that you calculated here is the same as what you could have calculated on a full wave. So let's calculate our VDC. So from our formula, we saw that VDC is equal to Vmax. Just going to rewrite it also. That's Vmax into 2FC. So the other formulas, they are limited. Not to say they do not work, but for this question, they do not work. They are limited. But this one is going to work. For a full wave, our VDC, we saw that it's given by the formula Vmax into, it's going to be 4 FCRL over, it's just going to repeat everything in this case, then we add a 1. So this is it. Let's calculate for a half wave. You're going to substitute in this case the maximum voltage we obtained. That's our maximum voltage, 67,872. Then in this case, the frequency, everything is there. So 2 times the frequency. Remember, our frequency is given as 50. That is, we've got a 50 hertz, and the capacitance, our capacitor, has got a value of 4,400 microfarad. So this is going to be times 10 to the exponent of -6. That is 4,400 times 10 to the exponent of -6. And our RL, which is our load resistor, 440 ohms. So we have got our resistance in this case. So as you can see, this here is a repetition. We're going to repeat it as it is here. So it's 2 times 50 times 4400 times 10 to the exponent of -6 times 440. Then we add a 1 plus a 1. So that is what we are going to have in this case, which is going to give us the VDC of 67. If you calculate properly, you're going to obtain 67,523 volts, something like that. Which in this case What is just going to change on a full wave? Because remember, this side you are working with a full wave. On the full wave, what is just going to change is the 4 here. Everything is going to remain as it is. The maximum voltage, the one that we obtained, then that's going to be 4 times the frequency, which is 50. Capacitance, everything is just going to remain as it is. In that case, times 10 to the exponent of -6. Your load resistance being 440. All right, so this part is a repetition also here. So that's 4 times 50 times 4400 times 10 to the exponent of -6. That is, we are going to add a 1 later on. There we're going to add a 1. So this is what you're going to have at the end. And that was going to give us our VDC, which is 67,697 volts. So that is what you're going to have in that case. So as you can see, these values, they are going to differ for a full wave and a half wave because of what? The formulas that you are using. So that's our VDC considering a half wave. All right, so since because of other calculations that you might actually have later on, we might need these values that we are seeing. So I'm just gonna take this part just for the sake of revision so that we take this into consideration. So we obtained our VDC, this side 67.523. Okay, then this side of a full wave, that is 67.697 volts. All right. So like I said, we might need these values later on. Let us just keep them aside and check the other question. That is the load current in that case. All right. Remember the load current, you must understand this, guys. Formulas are already there. But what is the idea of the load current and this VDC? This is at the output. So the load current will be where VDC is and where RL is. So simply the load current is VDC over what? Over RL, provided that we have got what? We've got VDC and we've got the load resistance. We can use that formula. Also here, we stated that if you still remember on your formulas, so that you just get rid of your formulas again here. That's VDC over RL. So in that case, we calculated the VDC. We have it. The load resistance is there. So meaning to say we can calculate our load current in that case. All right. So the load current is going to be VDC over RL. So for a half wave, remember our VDC is this one, 67.523 divided to the load resistance, which is 440. That was going to give us our load current of 0,153 in that case. This is measured in amps. If you are to work from the full wave, the formula is not going to change. We are still going to obtain the same formula for that is VDC over RL. But what just changed is the value of your VDC. Remember, for a full wave, this is the value that we got, 67.697 divided. The load resistance is still the same. So that was going to give us the load current of 0,154 amps. So as you can see, it won't be that much different. Even if you check the VDC, the values are just almost the same. Not exactly the same, but they are almost the same. So that is, we can use this value. We can apply or use our current. Okay, in case that we're going to need these currents, we are going to simply apply our formulas. Let's check, our values. Let's check another question. Number 3, the ripple factor in this case given by what? By gamma in that case. Like I explained, that the ripple factor depends with the textbook that you're using. Some, they use the letter R, as I stated on the introduction. You can use the letter R or you can use the letter gamma, all right? So that is, if we were having, let's say we have got the ripple voltage, we're going to simply use this formula, but we do not have in that case, all right? Let us check what we are given in that case, because if you're to check you have to consider this other part here. They're actually asking you to calculate the ripple output voltage here after this number 4. So meaning to say on number 3, this part of the ripple factor, they do not want us to use this because as you can see, the VRMS, they want us to calculate it later on. So meaning to say, we are not having this one. So we are going to focus on these other formulas here. We have got the load resistance, the capacitance, so you can use these formulas in that case. Remember, this is for a half wave and this is for a full wave. So that is, we are going to apply these two formulas in that case, all right? Because we are not having the ripple voltage. They're actually asking you to calculate that ripple voltage on the next question. So it's a sign that they didn't want you to apply this. They wanted you to apply the second one. All right, so this is it here, number 3. So our ripple factor is given here. They are using the letter gamma. So gamma is equal to what? So on a half wave, we saw this is 1 over, that's 2 square root of 3 into the frequency, the capacitance RL. When it is a full wave, we are going to have our ripple factor as gamma is equal to 1 over 4 square root of 3 times the frequency, capacitance RL. So that is, there are different formulas in that case. Okay, so we can calculate our ripple factor in that case. So using gamma in that case is going to be 1 over 2 square root of 3. The frequency, everything is there. The frequency is 50. The capacitance, remember, 4,400 times 10 to the exponent of -6 times our load resistance, which is 440 ohms. So that is 440 here. So that was going to give us our ripple factor, which was approximately 0.003. All right, actually, there are so many values that are there that you can consider, but you can also just write it like that. Then on the other hand, we can calculate it for a full wave. For a full wave, we're just going to have a 4 in that case. In place of these two, we are going to use a 4. So this is 1 over, that will be 4 square root of 3 times the frequency. Every part here is going to remain as it is. That is 50 times 4,400 times 10 to the exponent of -6 times 440 in that case. So that was going to give us approximately 0.01 as our ripple factor. All right, then from there, we can calculate now the ripple output voltage, which is the RMS ripple voltage. From which formula? Because we have got the ripple factor and we also have the corresponding VDC. So meaning to say, from the formula that we are used to, remember we used to have this as given as VDC, because we can just make this the subject, cross multiply. So it means our ripple voltage is going to be equal to the ripple factor times our VDC. In this case, our ripple factor, which is gamma, times VDC. So meaning to say, we can simply use this, and this is going to affect even this side, but only that what is different are the values that you are using. As we can see, we have got different values of what? Of the ripple factor in that case. But the formula is simply going to be the same. So VDC is there, our gamma is there. So meaning to say, they're going to simply multiply. That is our ripple factor, 0.003 times our VDC, which is 67.523. That is, we are going to obtain our RMS, our ripple voltage in that case, which was going to be 0.203 volts. On the other hand, what is just different are the values here, but the formula is simply the same. So it's going to be 0.01 times, remember your VDC on the full wave, it was 67.693. So it's going to be 67.693. That is going to give us approximately 0.068 volts as our ripple voltage for the full wave. So this type of a question is for you to understand that the formulas are not exactly the same. you must consider in an exam, because they are not going to give us exactly like this to say this is half wave and full wave. They are going to give us one of these. Is it a half wave? Is it a full wave? So the formulas are the ones that we stated before. You must use appropriately the formula that you are given according to the information. All these formulas, they are going to be applied depending with what you are given. All these formulas, it's not like we are going to be using this formula always. We used this formula sometime. We have applied that we use this formula. Now we are using this formula. It's because of the information that is available there. So I need us to work with more questions. Just try to revise even your typical exam questions and see how are they going to ask these questions on a shunt capacitor filter. You must be very careful of the two types. Is it half wave or is it a full wave?